so today we're going to be talking about ARM firmware reverse engineering. The idea here is that you have a small embedded system. We're talking something too small to run Linux or Android, something that has no memory management unit but is still running the ARM architecture. ARM is also used by Android, by iPhone, by some of the Chromebooks. And so there's lots of open source tools that you can use for ARM on the bigger system that also apply to things that you might find in the smaller system that can aid you in reverse engineering. So the specific example that I'm going to be using is a ham radio, a handheld digital ham radio that I've been reverse engineering. Show of hands, how many of you have reverse engineered something from China? Malware does not count? Okay, a few hands stayed up. So I took a Chinese amateur radio and I started writing Linux tools for it. And as I was writing them, at some point I typed in the commands wrong, and instead of sending me back a copy of its settings, it sent me back the beginning of firmware. It turned out this was a null pointer dereference read that was unindexed, which was exploitable and could be used to dump out the firmware. The firmware dump could be used to turn JTAG back on. JTAG could be used to dump a complete copy of all of the firmware. XORing the complete copy of all of the firmware with the encrypted firmware update gave me a clear text key that I could use to encrypt or decrypt any other firmware image. And then by reverse engineering this and patching it, I was able to add new features. So we have a phone book of all 35,000 amateur radio users of the DMR protocol that is held inside of the radio, so that when you have an incoming call, you see the name, call sign, city, state, and country of the party on the other line. This protocol is internationally trunked, so you can make calls between countries. It's not yet popular in Serbia, but it's very popular in the United States, in France, in South Africa. And when it reaches Novi Sad or Belgrade, you'll be able to make calls to all of these countries without a cell phone and without any commercial infrastructure. Since I started the project, I was joined by Paula, who's DD4CR, Alex, DF8AV, and David, AB3TL. In the United States, my call sign is Kilo Kilo 4 Victor Charlie Zulu, but here in Serbia, it's YU/Kilo Kilo 4 Victor Charlie Zulu, as I'm roaming. The purpose of this lecture today is not to talk about the ham radio, although I love the ham radio and I would be happy to talk about that a lot after the lecture. The purpose is to actually talk about how you reverse engineer these embedded systems, because I've already reverse engineered this radio, and the only reason you would give a damn about it as a target is to add new features to this project, which you're free to do. All of the code is on GitHub, and we welcome new contributions. But that's not why you're in the audience today. You're in the audience here today because you want to learn how to do this on your own machine, your own target, hardware that I've never heard of. So the tricks that we'll be talking about are sort of designed to work on other targets. I'm going to be teaching you how to extract firmware through a null pointer dereference that is unindexed and only a read. This is not exploitable on desktop Linux or Mac or Windows, but it's very often exploitable on embedded ARM, because embedded ARM likes to put a copy of the code at address 0. So it's legal to read from address 0. Whenever you have malloc returning a 0 and you try to read from it, you get a copy of the firmware. Whenever you write to that, the writes are silently ignored, which is a very convenient way to rip software out of protected devices. I'm going to teach you how to reverse engineer an embedded USB stack, how to reverse engineer weird networking protocols. In my case, the DMR, or digital mobile radio protocol, is used for voice and for text messaging. And it's weird. It has 3-byte addresses. So it has 1/256th the number of addresses that IPv4 has. If we all try really hard, we can fill it up. There are only 24 million to go around. I'll be teaching you how to recognize I/O addresses and the few constant points of reference that you have in an embedded system because you don't have symbol names. They're not included in the firmware as it's written into the device. I'll also be talking about China and how great it is to reverse engineer Chinese things. For example, if you're reverse engineering a Western product and you want a copy of the schematic diagram, well, you have to take apart the board, you have to sand it down, you have to photograph it, you have to recover the photographs. It's a lot of work. If you want to reverse engineer a Chinese product, you write an email to the manufacturer and you say, hey, David said that I could have a copy of this. Could you please email it to me? And they will. I'll also be talking about how to port symbols between different firmware versions. When you're writing and maintaining patches to something, as opposed to doing like a one-off patch or a brief product, you need to be able to upgrade your patches to work on new versions. And the more functions you tie into, the more labor that involves. So you would very much like to automate it. And it turns out that for embedded ARM, it's very easy to automate these symbol conversions. And then, you need test cases. You need to be able to ensure that your code still works on every version without manual testing, without having to boot it up and exercise every feature. For this, it turns out that Linux is awesome because QEMU allows you to run foreign Linux executables, like for other architectures. So you can make an ARM Linux binary and then run it on AMD 64 as is without any changes. And I'll be teaching you how to do these things in the course of the lecture. The radio that I'm using is this model. It's the Titera MD380. When you transmit with this model, it transmits either analog or digital. And you can hit an analog repeater or a digital repeater, and through the digital repeater you can send compressed audio using half of the time slots. So you can have two conversations on the same radio repeater. It transmits with 5 watts. This is a hell of a lot more powerful than any Wi-Fi card you've ever had. You don't really need a Yagi or direct line of sight to the tower. This is the sort of thing that you would have in a taxi cab or a handheld police radio. And with that much power, you get coverage indoors. So even though there's only one tower in this city, and that tower is rather far away, and the tower itself is blocked by all of these walls, by the infrastructure of the building, if I transmit, you'll actually hear the tower come back. And if I said hello, they would say hello back, and legally I probably should have just identified myself. Now, it can do either digital or analog traffic. The analog is done for backward compatibility, which is how it connects to the tower that's been here for a dozen years. The digital towers are rather new. They were originally used for broke police departments and for universities and dump trucks and that sort of stuff. But now that the cheap radios are available, they're filtering down to amateur use. You can take a test at the local amateur radio club, get a license and hop on the air, and freely use this as a replacement for cell phones. The hardware in this device is the STM32F405, which is a 32-bit ARM core. It does not run the ARM instruction set. It runs a reduced instruction set called Thumb. Your cell phones, which are ARM, run both instruction sets. And the way that they know which is that if the program counter is odd, it runs Thumb code, and if it's even, it runs ARM code. And this way you can have 2 instruction sets simultaneously existing inside of the same program. You can bounce back and forth between individual functions. It has 1 megabyte of flash. It has 2 different regions of RAM. One of them is 128 kilobytes, and the other is 64 kilobytes. Combined, you get 192. But the C compiler really doesn't like RAM to be split up this way, so it only knows how to allocate it in one region or the other by the linking script. The radio baseband is a custom Chinese-designed ASIC chip called the C5000. This is different from the Texas-designed C5000 chip, which is unrelated. And you sort of give it either your audio frame or your data frame during the time when it's not transmitting, and then in the other half of the time it does the transmission. And the opposite on reception. But you're always using that idle time. And this way you can have two conversations running at once, but the radio is only able to participate in one of them. So you're not going to get stereo sound or to be able to transmit and receive in the same conversation at the same time. So you have to physically push the button to transmit and release it to receive. It also has 16 megabytes of SPI flash. And the reason why they use 16 megabytes of SPI flash is that a 16 megabyte chip is a lot cheaper than the 1 megabyte chip that they designed the firmware for. So 15 megabytes are unused, and this is where we store things like our caller ID database in order to display all of the incoming contacts. A network for this protocol is very large. This is a map of Tennessee, which is where I'm from. In the middle is Nashville, which is sort of like our Belgrade, and toward the right, in the middle of that big green area, is Knoxville, which is our best city and our equivalent of Novi Sad. It's like a university town with very good beer and friendly people, although most of the Turbo Folk concerts are in the bigger city to the west. This network has 6 towers. They're bigger networks, of course. But through these 6 towers, you can transmit to any one of them and be heard through the others. So my friend Josh is in Nashville. If I'm in Knoxville, I can transmit to my local repeater, and it will route that traffic through the internet, and he will hear me on the other side. You can do either group calls or private calls, and you can also do text messaging. The radio supports cryptography, but not very good cryptography. Of particular interest is that the audio cable, the pinouts for which I show here, also contains USB. And it's not a USB to serial chip like many other amateur radios. It's actual USB implemented on the STM32. You can reprogram this chip to do mass storage, or pretend to be a printer or a hard disk or whatever else you like. You could boot from it if you cared to. So as part of my reverse engineering, I wanted to figure out how to capture packets for it. There was no packet sniffing hardware available when I began this project. So I wrote a series of Python scripts combined with firmware patches that allow you to do things like dump text messages. So this is a text message that I sent from one radio to another. And the contents of it is ASCII with a couple of accent marks. So it's 16-bit wide ASCII instead of 8-bit wide ASCII. But it's not encrypted. Even if you enable encryption for the channel, the Titera radios, the ones that I've been reverse engineering, leave all of the encrypted traffic clear text. The same thing happens with audio for all of the metadata. So even if you couldn't break the crypto, you would still see what my source address was and what my destination address was. If that's not enough, the most common audio frame that you get is actually the silence frame. And the cryptography is, it wasn't designed to be this way, but in practice, it's a very secretive algorithm called exclusive OR. And so if you just XOR with the silence frame, which is all zeros, you can recover the audio. I also wanted to be able to communicate with this radio like from my phone as I'm wandering around, right? I didn't want to have a laptop to do all of this. So I wrote an Android application, which you can see in this blurry photograph here. And the Android application is actually able to do everything that the desktop software would do. So you can reprogram the radio, you can dump out the frames. It's still a work in progress, but as soon as this is finished, it will be publicly available in the App Store for free, and you'll be able to have your crappy Android phone talk to your radio. Now, in reverse engineering software for a PC, you have a lot of advantages that you don't actually get on the radio or on the embedded system. One of these is that when you're reverse engineering something on a desktop, almost always you get a copy of the executable for free. And if you don't get a copy of the executable for free, then you get it through an unpacker. So at some point there is a process which you can rip out of your operating system, and your operating system will help you to do it. In embedded systems, you don't have a copy of the code. You only have the physical device. And it has a USB port or maybe a serial port that you can talk to, but it's usually defended. So they will lock JTAG so that you can't connect a debugger. They will lock the bootloader so that you're not allowed to read anything out until you erase everything. My favorite method for ripping firmware out of these devices is to exploit the bootloader. And my second favorite method is to exploit the regular application through an unindexed null pointer read. A null pointer read is when you have a pointer to address 0, and the software reads from that address and gives you the result. On Windows or on Linux, there's a guard page at address 0, and if you try to read from it, it will trigger a segmentation fault and your program will crash. On embedded systems, it doesn't do that because there's no memory management unit to actually trigger the crash. So what happens when you read from 0 is whatever the hell the chip defaults to. And to make it very convenient for compiler writers, embedded ARM maps a duplicate copy of flash to address 0. So if you read from it, you get a copy of the flash. So you have this uninitialized pointer that sticks to address 0. On Windows, this would trigger a fault. But in order to exploit it on Windows, you need an offset. You need to be able to say, no, I didn't want 0. I want the 16 millionth item in the array that begins at 0. And that will read far enough up. In the Cortex-M4, because there's this uninitialized buffer pointing to 0 that you can read from, flash, which is normally at 0800 and change, gets duplicated here. And if you read from it, you get a copy of it. So null pointer pages don't actually trigger a fault when you read them. They give you a copy of the code. And you can recognize that it's the code because it begins with the interrupt vector table, which is a series of addresses for the interrupt handlers preceded by the initial stack pointer. The initial stack pointer is always in RAM. The interrupt handlers are always in flash, and they're always thumb code. So you wind up with a single number that's above 2000 and change, and is even, followed by many numbers that are at 0800 and change and are all odd. So the radio speaks a semi-standard protocol called DFU, or the USB Device Firmware Update Protocol. This is the same protocol that was exploited in the iPhone 3G for the Lime Rain exploit. So when people would jailbreak their iPhones, they would exploit the same protocol that we're exploiting here. The protocol allows you to read and write memory pages, but there are multiple memories that you read from. So in the MD380 implementation for the radio that I'm attacking, you can actually specify which radio you'd like to read from. And if you don't specify any, then it defaults to address 0. So the buffer is null, and when you read out of it, it begins at 0, and the maximum amount you can read is 48 kilobytes. It just so happens that the first 48 kilobytes are the bootloader that decrypts the main firmware image. This is even better than having a copy of the main firmware image because this is the code that actually decrypts it. And it's also the code that's responsible for locking JTAG. So I can change 1 byte of this program, write it back into a fresh, brand new chip, and have the exact same bootloader with the exact same behavior, and the only difference is that it never locks debuggers out. So then I can install a firmware update, attach a debugger, and read out a copy of all of the code, allowing me to read all of the firmware. So I had a friend of mine visit town. She comes to town, I give her a copy of the code base, and in the course of a couple of days, she realized that the firmware update was using AES in counter mode. Counter mode is where you use the AES encryption algorithm as a random number generator, and then you XOR those random numbers with the data that you want to keep secret. The bug was that they repeated the position in that random number stream every 512 bits. So for every block of memory that was being read or written, they were XORing it with the exact same key stream. So if you just XORed one block of this from the encrypted firmware update with the unencrypted firmware update, you would get the key. And then you could XOR that with anything else to encrypt or decrypt it, same operation. And this allows you to then decrypt the official updates from the manufacturer and re-encrypt them to run, to re-sign your own code so that it will be installed by the official factory update protocol and firmware. So at this stage, we no longer need to modify the hardware or use our own hardware. We can just reuse the existing manufacturer hardware and software and protocols. But it's at this stage that you need to begin reverse engineering it. So how do you find the useful parts and how do you figure out what they do? And then having found them, how do you make changes to them so that your code instead of their code runs at just the critical portions? For example, you might find the function that matches an address and then patch that to accept all addresses in order to enable promiscuous mode, which, as you will recall from Wi-Fi, was pretty fucking handy in actually being able to exploit vulnerabilities in Wi-Fi that prior to 2006 were kind of untouchable. The first thing you need to know is where things are in memory. Unlike Unix or Windows, where you have a varying memory layout per process with address-space layout randomization moving things around, on an embedded system, everything is stuck at a fixed physical address. And there is no such thing as virtual memory. So all of the I/O ports, when you read from a serial port, when you write to a serial port, when you access the USB controller, all of those addresses begin with a 4. And most of your RAM begins with a 2, except for a smaller region of faster RAM that begins with a 1. The faster RAM is called tightly coupled RAM. It's connected directly to the data fetch bus and to the data fetch cache, I mean. So it's actually faster to read from than the SRAM is, but it's not connected to the instruction path, so you can't actually execute this code, and you can't DMA it. So if you try to, for example, send a USB packet out of tightly coupled RAM, it doesn't work. You have to send it out of SRAM. And all of those begin with a 1. If it begins with a 08, it's in flash. The bootloader is from 080040 to 0800C 3 zeros. At 0800C1000, you have the actual application. This is the piece that we're interested in changing because all of the code at this address is what runs after the radio has turned on. The bootloader is only involved in firmware updates and in the initial startup process. In IDA Pro, which is hellishly expensive but very effective, all you need to do is get a copy of the firmware dump, load it into a process, and then tell it that it should have RAM at the location where RAM should be. So in this screenshot, I'm telling IDA that RAM starts at 2000 and change hexadecimal, and that ROM starts at 0800C000. And then I give it a copy of the binary firmware image that I've extracted from a firmware update. By doing these through a firmware update, I can use the manufacturer's own publicly released files, and I never have to leak any confidential information myself or extract this information from a physical device. Now, IDA Pro is very, very expensive, but there's a free competitor to it called Radara 2. There was a conference these past few days in Barcelona where they were, all the developers of Radara 2 got together and added new features. There are some tricky pieces to it. The first is that you have to run today's version because they fix bugs every single day. Every time you sit down at your laptop, you grab a new version and then you build it and then you run it. It's used from the command line with an optional web interface. This is the command that will load my firmware dump as a 16-bit image to the correct address as an ARM application. Now, the first thing that you need to do is you need to find useful functions. If we were on a PC application, we would look for things like printf, maybe hunt all of the printing of error messages, and then work our way backward in order to figure out which functions called them and what those functions do. In embedded systems, you don't have error messages. If it crashes and tough shit. But what you can track are the I/O addresses. So I know that all of the I/O addresses begin with a 4, and I have a complete listing of all of them from ST Microelectronics, which is the manufacturer of the CPU. And these are the same for all units of that CPU. So I know that the flash controller begins at 402300, and I know that the flash protection register, which disables the write protect field, is at 4002-3C15. So if I search through all of memory for an access to 4002-3C15, I know that that function is being used to either enable the write protection or disable the write protection of the flash. Its parent function is probably disabling the protection and then writing the flash and then re-enabling the protection. There are similar features for the serial port. More recent models of this have a GPS receiver in order to get their GPS coordinates. Well, that GPS receiver is connected over a serial port, and by looking for the serial port's address, I can identify all of the GPS code. You can also look for unique masks. So this is a 32-bit architecture. Every register is 32 bits wide. But the DMR protocol uses 24-bit addresses. So it has to mask off the biggest byte whenever it's reading an address out of memory. So I can identify everything that involves the addressing in this unique networking protocol just by looking for all of the code that contains 0x00FF. There are similar masks for other features. When you have something that's maybe a 7-bit field, you'll see a mask against 7F. And this allows you to identify all of that code. Now, you can also look for particularly awkward implementations of things because you have multiple authors who write libraries, and then those libraries are statically linked to create one firmware image. For example, DMR uses a proprietary audio compression codec called AMBI+2. There are lots of hard feelings about this audio codec because even though the patents have expired, the company has made pretty clear that they will sue anyone who doesn't give them a licensing fee. So it would be really handy to understand this codec or maybe re-implement it. Now, AMBI functions use shorts, 16-bit fields, in order to store bits. And they do this because someone, when writing the code, created an array of shorts because that was particularly efficient on his architecture. On this architecture, not so efficient. There are better ways to do it, but that's still the way that it was done. So any code that's actually referencing an array of shorts is probably related to the iambic codec because there's no other reason to use an array of shorts. You can also look through memory, find every array in which all of the 2-byte fields are zeros or 0001, and anything that touches that data is the audio codec. It's also handy to reverse engineer the USB stack. So the USB stack is by a different author than the audio codec and the main application. They used a nifty trick here, which was that they took the example USB stack from the manufacturer and then they reused that. Well, when you do this, the source code is available. So unlike the rest of the radio, you can actually go to ST Microelectronics' website and get a copy of the example that was forked for this project. This then tells you how it's architected, all of the data structures, it gives you the header files. It's lovely for reverse engineering. So you see that the handlers are function pointers. Function pointer called functions are sort of like misinterpreted by IDA Pro and Radara 2 in that they're not called by anything. So the auto analyzer won't find them. So you just look at the gap between functions, and that's where your USB handlers are. So in order to find them, you search through RAM for pointers to flash memory. You'll find these for things like graphics, because if you have a sprite, you want a pointer to the sprite, and the sprite will be in read-only memory. But the functions are data, and the functions are code, and the sprites are data. Data is at an even address, code is at an odd address in this architecture. So you can use that to throw away all of the data references and give you only the function pointers and all of the function pointer targets once you get a dump of RAM. You can also look through the decompiled code after you've identified these functions and look for the 1-byte commands that are used in their implementation of the USB device firmware update protocol. So in my case, I know that there are special manufacturer commands for 2.1, 4.1, A2, 9.1, and C4. Well, how many functions in this code base reference all 5 of those bytes separately in if statements? Turns out there's only one. The decompiler is able to identify that and to show me all of the code that references these regions. You can also do, you also need to do function hooking, because once you've identified the USB stack, you don't want to make minor changes to it in assembly language, because that is a ton of labor and it's not portable between versions. What you would much rather do is write your changes in C. So what you do is you rewrite all of the function calls to run to your version instead of the manufacturer's version. Now, for runtime function pointers like the USB stack, there is a 4-byte address in RAM, and you just need to change those 4 bytes to point to your function instead of the original. And what you'll usually do is you'll have an if statement to see if you should manage that function, and if not, you run it over to the manufacturer's version. For non-function pointer calls, when they actually have the machine code to call the particular address, in Thumb, these are done through the BL instruction, or branch and link. Branch and link is secretly 2 instructions in a row, the first of which loads the upper part of the address and the second of which loads the lower part. The alignment's a little bit confusing, but you can write 2-3 lines of C that will actually calculate this offset, and then you can run through and identify all of the calls to a particular offset and then patch them. Now, you need room to put your code. So there's 1 megabyte of flash, internal flash that you can execute code from. There are 16 megabytes of external flash, but you can't execute in place for that, so it might as well not be there. But this is a Chinese design. So in the 1 megabyte where they've taken all of the memory and used all of it, a fifth of that, 200 kilobytes, is the Chinese font. Now, you can cut this out, and the only side effect is that you see random crap instead of Chinese letters. So you cut that out, and you see random crap instead of Chinese letters, and then you use the Latin alphabet instead, and you're good. So this allows you to then have a complex C compiler with a lot of code and plenty of memory left over as far as the code goes. You also need room for your own RAM, because these 200 kilobytes are executable and they're readable, but they're not writable, or they're not quickly writable. So you need to find unused RAM, and the way that you do this is you realize that there are 2 different RAM regions. There's one that begins with a 1 and another that begins with a 2. You overwrite all of this with a string that you can look for later. In my case, I used dead beef. I'm wondering if there's, you could overwrite all of it with tsetsa, like tsetsa, and then check back afterward in order to see how much of that got damaged by the main application. For example, the main application has global variables that it initializes to 0 at the beginning. Well, all of those will be overwritten, and you won't mistake them unless the author of that application also thought it would be a great idea to have a large region with tsetsa. There's no G, but maybe the 6 is close enough, and you could do goga. So you paint this before you actually enter the manufacturer's firmware by overwriting all of the words in RAM with it. And then after you've started the manufacturer's software, you then dump out all of the RAM over, say, USB. You then look for large continuous chunks of Goga Goga or Tsetsa Tsetsa, and you'll find that 20 kilobytes of the tightly coupled RAM are unused. So you tell your compiler to target this region, and then you can overlap your firmware with their firmware and have a completely functional combined application. At this point, you have a proper C compiler. You can redirect function calls from the original firmware, and you can call back to the regular code, and you're good. You're golden. Until some jackass releases a new firmware version with a killer feature like fixing a major bug or adding support for GPS, which is what happened to us after about 9 months of no firmware updates from the manufacturer. They forked the hardware once in order to change the audio codec and the copy protection chip for the audio codec, which was the very first time in this project that we found the copy protection chip or realized that it was a thing. And then separately, they did a fork to add GPS support, and they did these at different times. So there are now 4 variants of the hardware that have the exact same model number that are sold through the exact same distribution channels, and we have to support all of them. The way that we did this was through building a tool to port the function addresses. Now, this is an ARM application, but suppose for a second that it were AMD 64. This screenshot is from a tool called Binary Ninja, which is a much cheaper reverse engineering tool than IDA, and much faster, but does not yet support ARM, so you'll have to wait 2 or 3 months before you can use this for embedded targets. In AMD 64, when you have these calls, you have lots of addresses being loaded that are adjusted by the linker. In this case, you have the 49 opcode that's loading an address into the R8 register. You have the 48 opcode that loads it into the RCX, and then you have another 48 that loads it into the RDI. You need a good disassembler in order to compare this function to the exact same function from another application or another version. Because all of these addresses, libc csu fini, libc csu init, main, libc start main, all of these addresses get retargeted by the linker and changed to new addresses. So the bytes of the functions will not equal each other. In ARM, this screenshot is from Radara 2. In ARM, you can do a lovely little trick to get around this, which is that ARM does not have as many ways to load an address into a register. Thumb has even fewer ways. So these 3 lines at the bottom, 1044C, 10450, those are what's called a constant pool. Because in ARM, and even more so in Thumb, the immediate addresses are very awkward and difficult to use. So instead of using immediate addresses, they do program counter relative addressing. They say, hey, 16 words further is the word that I want loaded into this register. Which means that all of the data addresses get shoved to the end of the function and aren't in the middle for you to have to disassemble and skip. And the only exception to this is the function call, or the branch and link instructions. Now, on Thumb, all of the branch and link instructions have an F as their first nibble. And the remaining 3 nibbles don't matter. Thumb instructions are 16 bits wide instead of 32 bits wide. So if you want to compare 2 Thumb functions for equality, all you have to do is compare all of the 16-bit words together, and you consider it a match if either they are perfectly equal or if the first nibble is an F in both of them. And if so, you continue along. This is enough to identify any functions that have been relinked. So for example, a vendor library that's being thrown in, or a C function that's being compiled with the same version of the compiler. And this code here A quick little do while statement is all that's required to actually do the comparison and give you a score for equality. If the score is more than 10 or 12, and it's the highest score, it's always a proper match. No false negatives. One other thing that you would like to do, it's one thing to be able to patch the firmware and run it in the radio. So I take my radio, I turn it on, I make a phone call to the repeater, Billy Bob calls back to me and says that he can hear me fine, and then I know that I have not fucked up the audio. But when I have to support multiple target firmware versions, and my code has to be bug-free, or Billy Bob will call all of his friends and they will all file separate support tickets on my issue tracker, I really, really need to make sure that I can test my code automatically rather than having it be tested by the poor user who tries to run it first. So I made this tool, which is called MD380EMU. MD380EMU is the firmware for this radio recompiled to run on Linux. And the code to get this working is very, very small. We're talking 2 pages. The trick for this is I begin with an ARM Linux executable, something that you might run in a Debian shell on an Android phone. There's a system called mmap. Mmap allows you to map a file into RAM. This is what you use when you have a file that's much larger than RAM, but you need to randomly seek inside of it. And you need it to be at a particular address. I don't actually remember the historical reason why you're allowed to specify the address, but you are. So what you do is you tell it that you really want the firmware file mapped into memory at the exact same address that it would be in the radio firmware. And then you can call all of the functions inside of the firmware. And as long as they don't require a hardware feature that's in the radio, but not in your phone, they still work. It can run the same instruction sets. It can run the same vector additions. All of the audio codec still works. You can also use obj copy to take the firmware image and then copy it into an ELF linkable module, and then you can link those modules together in order to have a regular ARM Linux executable that, that contains the firmware image and is able to execute all of the functions that are in that image. These are the same functions that you've reverse engineered in order to interact with the code in your patching. If you could turn the audio on. Okay. So the other thing that you can do is you can then take this code and you can use it to turn any of the libraries that were used in the radio into libraries that you can use on your desktop. Because, now I told you that this was an ARM Linux executable, but my laptop is AMD 64. There's this convenient little tool called QEMU that is like normally viewed as a poor man's competitor to VMware or VirtualBox. But one thing that it's very, very good at is that you can run Linux executables from one architecture on a different architecture, and it transparently emulates it while maintaining all system calls. So your phone can use this to run proprietary software that was intended for your desktop, and your desktop can run proprietary software that was intended for a Raspberry Pi. In this case, my desktop is running the audio codec from the radio inside of a regular command line application that allows me to decode that radio image, decode the radio audio packets, and convert them into a standard WAV file.
Okay, 4 Victor Charlie Zulu testing.
So I can play the audio that came out over the radio on my desktop. I can then, without storing it decompressed or exporting the raw WAV file. This allows you to do things like convert music So for example, in that Goga song, she has that like annoying audio clip, sexy businessman. She says, no problem, right? So you can hook the encoding end and then convert the Goga sample to play at the end of every transmission you ever make from your radio. So that, you hop on the radio, you talk to Billy Bob for a while, and the minute you click off, the way that your radio will tell the tower you're done is that Goga Sekulic will say, no problem, and you're good. Those are the tricks that I have for you today. Cool. And this here is Mimine. She's a very good cat. Thank you kindly for your time and attention. Yeah. Yes. Okay, so the question was, how do I handle privileged constructions? You mean like user to system? Yeah. Okay, so the way that I handle user to system stuff is that embedded ARM developers, except for Matthias here in the back, don't actually use those features. So in my firmware image, everything is running in user mode. It never actually makes a system call. If they were to use these features, as my neighbor here knows, they could make the software a lot more reliable. For example, they could detect an access to address 0, and they could say, this is fucking illegal, I'm not allowing it, and they could fault. But they don't do any of that because in an embedded system, the application developer, the guy who is tasked with making the product and have the product ship on time, is very often the same guy writing the operating system. And he's not interested in making the operating system correctly. He's interested in getting to Hello World and then getting Hello World into a shippable product. So there are all sorts of nifty features in here that might be used that, as you're reverse engineering a product, you never find.
And you just map all the other memory, like memory mapped registers and so on, so that it doesn't crash?
Oh, no. So you can do that. So, for example, they might access the I/O registers that begin with a 4, right? And if I need to, say, implement the external SPI flash memory, which is accessed over an SPI bus, there are two ways to do that. The first way is to complete the emulator by actually handling the segmentation fault, recognizing the access to the I/O register, faking the results, and then returning. The other way to do that is to identify the functions that actually talk to the device. So SPI flash read, SPI flash write, and hook just those functions to run to my overloaded copy. And the particularly nice way to do that is to just map the code as a writable page. So that even though I'm not able to do runtime overwriting of the firmware inside of the device, I certainly can in a Unix process. And that way I only have to hook 2 C functions instead of having to hook 9 registers. You can do it either way though. Yes. Any other questions? Yep. Here in the front.
Thanks. So I have 2 questions. Is there anything you can add about China?
Oh.
And the second one is you mentioned something called TurboFoc. What is that? Tell us more about
that. So China is number 1. Mandiant is number 2. And TurboFoc has to reset the scale. So TurboFoc is indexed at 0. Cool. Thank you kindly. I'll be in the beer area if you have any further questions.